Hi, I'm Stan Yin from Sandal Medical School. I'm very glad to have this chance to give a speech at AIM 2026. Our research is Transformer-based Focal-Pairwise Attentive Ranking Network, abbreviated as TFPARN for anti-spoofing. As I don't have much time, let's just get straight to the point. Here's our table of contents, and we'll start with a little introduction. First, let's talk about the background and the practical challenges of our work. In recent years, AI-based speech generation has become increasingly realistic, which creates serious threats to automatic speaker verification system, abbreviated as ASV systems. At the same time, spoofing audio can have very different levels of difficulty. Some samples are easy to detect, while others are much harder. Conventional cross-entropy training may not give enough attention to these hard examples. Beyond accuracy, real-world ASV deployment also faces efficiency constraint. Devices may have limited hardware resources, users expect low-latency verification, and systems may need frequent retraining when new data is collected. Therefore, both inference efficiency and training speed are important for deployment and maintenance. Finally, for this task, ranking quality matters more than simple accuracy, because the system outputs continuous confidence scores rather than only class labels. The existing models either have good performance but consume a lot of time and hardware resources, or they are of type that saves time and resources but have a poor performance. Thus, we need a model that can balance performance and efficiency. And that's why we are proposing TFPARN model. This is the overall pipeline of TFPARN system. The input is first taken as a raw waveform, resampled to 16,000 Hz, converted to single-channel audio, amplitude normalized, and cropped or padded to a fixed 4-second length. During training, random cropping is used to increase data diversity, while development and evaluation use center cropping for consistency. After pre-processing, robust augmentation is applied only during training with a 15% probability. Then, each waveform crop is converted into log-mail features using STFT, mail filter bank projection, and logarithmic compression. These features are passed into TFPARN backend, which uses a transformer encoder for temporal modeling, attention pooling to focus on informative spoofing cues, and a lightweight binary classification head. During training, the model combines focal loss and pairwise ranking loss, so it can pay more attention to hard examples and improve score ordering. Finally, during development and evaluation, test time augmentation generates 5 fixed-length crops for each utterance, process them independently, and average their logits to produce a final anti-spoofing score. Let's look closer to TFPARN backend. First, each log-mail frame is normalized and projected into hidden feature space, and sinusoidal positional encoding is added so that the transformer can retain frame order information. The resulting frame-level embeddings are then processed by stacked transformer encoder layers. Through multi-head self-attention, each frame can interact with other frames, which helps the model capture long-range temporal dependencies across a full utterance. This is important for anti-spoofing because spoofing artifacts may only appear in short local regions, but judging whether they are reliable often requires broader context. After the transformer encoder, attention pooling assigns learnable weights to different frames and aggregates the sequence into one utterance level embedding. Compared with simple mean pooling, this allows more informative and suspicious frame to contribute more strongly to the final representation. Finally, the embedding is passed to a lightweight fully connected classifier, which output binary logits for genuine and spoof classification. Here's some mathematical mapping inside the TFPARN backend. Each frame is normalized and projected into hidden dimension. Then, positional encoding is added because the transformer is permutation invariant by itself and is explicit frame order information. After several transformer encoder layers, the output remains a sequence, so attention pooling is used to compute frame-level importance weights through a small scoring network. These weights are normalized by softmax and used to form a weighted sum of all frame representation. This slide explains why we use focal loss for hard sample-oriented optimization. Focal loss addresses this problem by adding a modulating term, y minus p sub t, raised to the power of gamma, to the cross-entropy loss, where p sub t is the predicted probability of the ground truth class. When a sample is classified correctly with high confidence, P sub t is close to 1, so this term becomes very small, and the loss contribution of that easy sample is suppressed. In contrast, when a sample is uncertain or misclassified, P sub t remains small, so the loss contribution stays relatively large. In our work, we set alpha equal to 0.5, meaning that spoof and genuine samples are assigned equal class weights. Therefore, the main purpose of focal loss here is not class balance weighting, but to emphasize difficult samples through the focusing parameter, which is gamma equal to 2.0. This is useful for anti-spoofing because some spoof utterance can sound highly natural, while some genuine recordings may contain noise, channel effects, or other artifacts. These ambiguous samples are more likely to lie near the decision boundary. By reducing the influence of easy samples and focusing more on hard samples, focal loss helps the model learn a sharper and more robust boundary between spoof and genuine speech. Pairwise ranking loss is introduced in our work. The motivation is that anti-spoofing systems are ranking sensitive. We do not only want each utterance to be classified correctly, but also want genuine trials to receive consistently higher detection score than spoof trials. To address this, we construct genuine spoof pairs within each mini-batch. Specifically, the samples are divided into a genuine set B and a spoof set S according to their ground truth labels. Then we construct all valid pairs from B cross C, meaning every genuine samples is paired with every spoof samples in the same mini-batch. The ranking loss is margin-based. For each pair, the loss is defined as the maximum between 0 and m minus the score of genuine sample minus the score of the spoof sample. In other words, the model is encouraged to make the genuine score higher than the spoof score by at least a margin. In our implementation, this margin m is set to 1.0. Finally, we combine focal loss and pairwise ranking loss into one objective. The final loss is L TFPARN equals L focal plus lambda times L pair. The coefficient lambda is set to 0.3, which controls the contribution of the ranking term. Next, let's talk about the experiments we conducted and the results. We chose to use ASV Spoof 5 dataset for training and evaluation. The difficulty lies in varying audio encoding methods, different levels of difficulty of each sample, and spoof utterance that employ various attacking methods. We selected RawNet2 model and Assist model as the baseline models. These two models well represent the existing models. The former trains quickly but performs poorly. The latter performs well but the training period is longer. We compare the models based on the following indicators. We use EER, minimum DCF, and actual DCF to compare the performance, among which minimum DCF is the primary indicator. We also use time to best model, GPU memory usage, and inference latency to evaluate the model efficiency. The lower these indicators are, the better the model is. This slide presents all indicators versus time graphs. What can be observed is that TFPARN model has the fastest training speed and performs better than other in all metrics. TFPARN model shows significantly faster decline and convergence speed for each indicator. The decline rate of the RawNet2 model in each indicator is also quite significant, but it fails to reach the same level as the TFPARN model does. The performance of Assist model is closer to that of TFPARN, but its indicator values fluctuate and do not show convergence. TFPARN model outperformed the baseline models in most efficiency indicators. It performs worse than the RawNet2 model in terms of time per training and inference latency. However, since indicators on TFPARN model converges more quickly, the total training time is actually shorter than that of RawNet2 model. The difference in inference latency between TFPARN model and RawNet2 model is not significant, but the performance of TFPARN model is much better than that of RawNet2 model. And the TFPARN system here only uses mean pooling and cross-entropy without pairwise ranking. After applying focal loss, pairwise ranking, and attentive pooling, the performance of TFPARN can be further enhanced. This has been verified in our internal ablation study of the TFPARN system. Now let's get into the summary part. Focal loss helps by reducing the influence of easy samples and forcing the model to focus more on ambiguous hard samples. Pairwise ranking loss further improves the score ordering by encouraging genuine speech to receive higher scores than spoof speech. Attention pooling helps the model select the most informative frame-level cues from the transformer output, instead of treating all frames equally. TFPARN runs fast mainly because its computations are regular and hardware-friendly. Most operations are standard matrix multiplications, multi-head attention, and feed-forward layers, which are well optimized by PyTorch and CUDA. Compared with graph-based models such as Assist, it avoids many irregular pairwise graph operations and heavy intermediate memory access. Also, since the input length is fixed to 4 seconds, the self-attention cost remains manageable. The main highlight of our study is that TFPARN builds a relatively complete anti-spoofing pipeline. Our study also considers training efficiency, which is important for practical ASV deployment. However, the current framework still has limitations. The front end mainly relies on log-mail features, so it may not capture local forgery traces strongly enough. Also, the current pairwise ranking loss is still a relatively simple formulation within each mini-batch. For future improvements, stronger local modeling modules can be added before transformer. In addition, the ranking objective can be further improved by using a more stable list-wise or differentiable ranking loss. Here are the references we used in this study. This is all the content. I apologize for my rapid speaking pace. It was too difficult to cover the research content within 10 minutes. In fact, it has already exceeded 10 minutes by a little bit by now. Anyway, thank you for your listening. Wish you a pleasant day.